Today we are going to be showing you valence shell electron pair repulsion, otherwise known as Vsepr theory. Vsepr theory is a theory that electron arrangements will form the most stable arrangement of bonds and that electrons will move them as far apart as possible from each other because electrons repel each other. Two types of pairs form this theory: bonding pairs and lone pairs. Lone pairs are electron pairs that are attached to the central molecule, while a bonding pair is shared between two molecules. These different number of bonds will create different shapes and angles.
For the pictures and videos that will be shown, the blue balloons represent the bonding pairs, and the green balloons represent the lone pairs. The green balloons are larger than the blue balloons because in reality, lone pairs take up more space than bonding pairs, and lone pairs will push bonding pairs closer together, creating a smaller angle between the bonding pairs. The central node, where all the balloons are connected to each other, is the central molecule around which the electron pairs arrange themselves.
This is an arrangement of two total bonding pairs. The shape is linear, the angle is 180 degrees, and one example of this is CO2.
This is an arrangement of three total electron pairs. Of these pairs, all three are formed by bonding pairs without any lone pairs. The shape is trigonoplanar with an angle of 120 degrees between each molecule. One example of this is boron trifluoride, or BF3. This is an arrangement of three total electron pairs. Of these pairs, two are bonding pairs and one is a lone pair. The shape is bent with an angle less than 120 degrees. One example of this is nitrogen dioxygen, or NO2. This is an arrangement of four total electron pairs. Of these pairs, four are bonding pairs, and none of them are lone pairs. The shape is tetrahedral, with an angle around 109.5 degrees. One example of this is methane, or CH4. This is an arrangement of four total electron pairs. Of these pairs, three are bonding pairs and one is a lone pair. The shape is trigonal pyramidal, with an angle less than 109 degrees. One example of this is ammonia, or NH3. This is an arrangement of four total electron pairs. Of these pairs, two are bonding pairs and two are lone pairs. The shape is bent with an angle less than 109 degrees. One example of this is water. This is an arrangement of five total electron pairs. Of these pairs, five are bonding pairs and none are lone pairs. The shape is trigonal bipyramidal. Molecules with five electron pairs have a rather interesting shape, being essentially made up of a trigonal planar shape with an orthogonal line running through the middle. The bond angle between the molecules in the plane is 120 degrees, while the bond angle between the plane and the two molecules above and below the plane, which form the orthogonal line, is 90 degrees. One example of this is phosphorus pentachloride, or PCl5. This is an arrangement of five total electron pairs. Of these pairs, four are bonding pairs and one is a lone pair. The shape is that of a sawhorse, or a seesaw. The angle is less than 120 degrees between the two molecules remaining on the plane. It is less than 90 degrees between the plane and the molecules forming the orthogonal line. One example of this is sulfur tetrafluoride. This is an arrangement of five total electron pairs. Of these pairs, three are bonding pairs and two are lone pairs. The molecule has a T shape. Like a T, the molecule has two electron pairs forming a line. This line isn't exactly straight, having an angle greater than 180 degrees between the two molecules. There is also a molecule extending downwards from the linear arrangement. This molecule has a bond angle less than 90 degrees from between the two so-called linear molecules. One example of this is chlorine trifluoride, or ClF3. This is an arrangement of five total electron pairs. Of these pairs, two are bonding pairs and three are lone pairs. The molecule has a linear shape with a bond angle of 180 degrees between the two molecules. One example of this is the triiodide anion, or I3-1-.
This is an arrangement of six total electron pairs. All six are bonding pairs with no lone pairs observed. This causes the molecule to have an octahedral geometry, with angles of 90 degrees between atoms on the x and y axes, and 180 degrees between attached atoms on the z-axis. An example of a molecule with this arrangement would be sulfur hexafluoride. This is an arrangement of 6 total electron pairs. 5 bonding pairs are observed, with 1 lone pair on the z-axis. This causes the molecule to have a square pyramidal geometry, with angles of 90 degrees between the atoms making up the square, and 120 degrees between the tip of the pyramid and the 4 other atoms. An example of a molecule with this arrangement would be bromine pentafluoride. The following model is also comprised of 6 total electron pairs, of which 4 are bonding pairs and 2 are lone pairs. This causes the molecule to have a square planar geometry due to the z-axis atoms becoming repulsive lone pairs. As the square part of the geometry implies, the bond angles are 90 degrees.
This is 6 total electron pairs, 3 bonding, and 3 lone pairs. It forms a T-shape with 90-degree angles and 180 degrees. This is not a stable arrangement, so you cannot find these naturally. This is 6 total electron pairs with 4 lone pairs and 2 bonding pairs. Forms a linear shape with a 180-degree angle. These are not stable, so it is not found naturally.
We hope this video has helped you in visualizing Vsepr theory's application to molecular geometry.